Hi everyone, my name is Odilon and today I'm going to talk about procedural shading for automotive visualization. This is the conference I did back in LA in April 24, but there was some problem with the recording, so I'm doing it again from home. And yeah, before I start, I would just like to thank Linkage, who sponsored the event, but also this presentation, as well as the other one I did about the future of automotive design and the use of Blender for that. So I'm really thankful that they helped us and they are pushing the community. Without further ado, let's just start. Quickly about myself. So my name is Odilon Loiez and I've been working as a modeler in the car industry, specifically in Sweden at Koenigsegg for 3 years, where I was doing hypercars, everything from the modeling aspect, basically from concept to A-class. And after this, I started my own studio with my friend Esa Mustanen, and we do all types of things from the design, the visualization, the modeling, and more we are switching to tool provider, basically. And in our work, we have to do a lot of visualization for our project or for client projects where we need to crank out a lot of renders quite fast. And so for this reason, we started to build our own library of materials so that we don't need to start from scratch every time. And so with time, we actually got to a point where we have our own collection, our own library, and we have almost 1,000 materials by now, which are based on a few shaders that we did that are entirely procedural. So we are not using any maps, which gives us a lot of control. And we are going to talk about that more. And yeah, actually, what are procedural shaders? First, we need to understand what is a shader. And a shader is basically just a small program that runs on your GPU. So it's just a piece of code that you send to the GPU to say, do this math, and this will tell you the color you need to put on that specific pixel so that you can show me something that I want to see. And procedural means that we're not using any maps for that. We're just creating everything out of math, basically. So we only rely on equations and mathematical operations to get to the result that we're aiming at. And so it creates those kind of weird trees sometimes. It's a bit discouraging to look at them the first time, but yeah, it's just creating a system that will get you the expected result. And so one might wonder, why would you bother making procedural shaders? Like, why not just using maps? And for me, there's three main reasons. And the first one is that it's really lightweight. First, in the file size, because you don't need to send any 8K, 4K, 16K map. So it's just text that says, do this math at this moment, and that will be the way you will know which pixel should be which color. And so it's very easy to just give it to someone. You can just, if you give the file, all the math will be already in there. You don't need to send separately the maps and everything. Plus, it's more lightweight for your GPU because you're not clogging it by sending a lot of data. I have this problem with my laptop where if I send a lot of 8K maps, I quickly clog the GPU and then it's totally unable to function. I just overload it, which is a problem. And with procedural shaders, I don't have this problem at all. Plus, I don't have resolution problem. Then the customization. Since you can describe exactly how you want through equations the behavior of the shader, then you can really do whatever you want. And the only limit is the time you will spend doing them, and also what is actually possible with the math. But you can go very far, and especially in the customization aspect, where you can create one shader that has some sliders and that will help you just decide like, this time the carbon fiber will be in this way, or I will want to have this pattern instead of that pattern, and you can just make everything evolve without having to plan what will be the options you will have. So if you would do that with maps, you would have different maps for different types of carbon fiber or things like this, whereas here you can simply have a slider, which is much more convenient and just gives like infinite possibilities. And the last thing is that if it's well done, you don't even need to bother with UVs, and you won't have any tiling or anything because you can add the variations in a procedural way. So that's also very helpful. Like, since you don't rely on maps, you don't have the problems that comes with maps. And so we will do a few case studies here. So the goal is that I show you kind of basically my journey to creating those materials. I think the metallic car paint is a good way to start, and we will see other examples later. And the goal is just to take you from the naive perspective that you could have at the beginning of like, I would guess you would need to start like this, to actually how to do it better. And yeah, just hopefully you can learn stuff on this journey. So yeah, let's start. So here we're in Blender, and so let's just switch to the shader editor. And yeah, the goal is to do a metallic car paint. So the first thing we need to do before we start is to understand what is a car paint. And the way a car paint is that you have two layers. First, you have this rough layer on top of which you add a clear coat that is very sharp and very crisp. Like it looks, it's really reflective. And so the most naive, the most basic way you would do that is just to take your principled BSDF, add some roughness, and then add a clear coat on top with 0 of roughness, and you get this result. But of course, that's not what we want. That's very basic. And so if we look a bit more into how a car paint is made, you can see that there are those flakes in the car paint. And so let's try to get those. So what we can do for that is to use the Voronoi texture. So this creates some cells, basically. It just puts some random points and then grows cells until those cells touch, and then it creates those polygons. Oh, it's not actual geometry, but this texture of polygons with random colors. And so what we can do is to just use that to create variations in the color, for instance, and also use the variations as just a roughness indicator. And that way we have this. And that's actually how I did my first versions of the car paint. And that's absolutely not correct, of course, but that's how naively we could think we can get to the result. So here we get some kind of variations that looks flaky, but we need to go a bit deeper in what actually happens on the flake level to actually be able to do something. And the reality is that each flake, since it's just like sprayed on the car, it has a random angle. So each flake is actually just some shape that just gives as a random rotation, and that way when the light will hit it, it will just bounce in a different way depending on which flake it's bouncing on. And so we need to find a way to be able to simulate those random angles. And conveniently, there is something like that in 3D, which is called normal maps. So we need to understand first what is a normal. And a normal is the vector, so just the direction, perpendicular to your surface. So if we take a plane that is on the floor, that vector would be just this yellow arrow that just goes up. That's the perpendicular. And so it means that if a ray bounces, it will just just bounce in a similar angle on the other side. And if I change the metallic and I give you this, we can see that it just reflects. But what we can do in 3D is to cheat that. And so you can see that we have 3 axes, which are blue, green, and red. And so those can be mapped on the actual 3D axis. So red will be X, green will be Y, and blue will be Z. And so what we can do is to start giving a direction to this vector, to cheat it basically, just by giving a color to the normal map. So if here I start playing with the orientation, you can see that it's changing the color of the plane, and this results. I'm using it as a normal map, this color, and this results in a different orientation of the reflection. And so we are just cheating. The surface itself is exactly the same, but we are just cheating the way it reflects just by feeding it this normal map. So on each pixel, we will say, actually, the normal of this surface is slightly more to this angle, like slightly more to the x-axis or the y-axis, and this will impact the reflection we have. And so we can use this thing. We can use this thing to do our flakes, basically. So if we go back here, we can just use the random color that is done by each flake and use that as a normal map to basically say, since the color will give the orientation compared to the basic normal that it should be, it will just give this random orientation per cell, which is exactly what we want. So here, if we just connect the color output of the Voronoi to a normal map, and then we connect that to the normal input of the principled, we can see that we get a result that is much closer to what we want. And that's basically the main behavior that we're looking for here, is this thing that each flake has a different orientation. And this will create this halo of light around each point, like light points, basically. So great, that's much nicer, but we can do a bit better. If you look here, the reflection, like the clear coats around this area, it's very desaturated, the orange, and also there's some weird stretching of the texture. So let's fix that here. The first thing we do is that we are using texture coordinate. In this case, I'm using UVs just because it's convenient. We'll talk about how to not use it later. But yeah, just doing that fixes the stretching problem. And then we can create just a simple setup where we are using a glossy BSDF, which is basically a metallic type of material. And this will be our first layer. And then we have the second layer, which is purely reflective. And we mix it with a Fresnel. And the Fresnel is just this effect that if you go very close to a surface with your vision, it will look more reflective than if you look at it just like perpendicular to it. And so then we get a much nicer visual thing for the clear coat, and overall it looks better. The next thing I want to change is the color, the shape of the cells, because I don't really like that it just looks like those random polygons, and it looks way too organized. They're just like next to each other, where in reality you would have some kind of overlap. And so we want to be able to translate this overlapping effect. So what we can do is that in the Voronoi, instead of just using the color output, we can start to play with the distance output. So as you can see, it just creates a gradient from the center of the cell to the outside. And so if we use just some mathematics, we can just say whenever it's under a certain value, you have it black, and if it's above, you make it white. And so through that, we can create a mask. And so we are able to just isolate basically the color of the cell just within a circle. And here they are colliding a bit, but that already gives us a nicer look. The only problem is that now there's a lot of area of this that is not used by flakes anymore. So it looks not dense enough. But we can simply just duplicate this setup that we have here and mix it together. And that way we can have much more density, and we have our nice flakes. And we also have this overlapping effect where it looks much more messy, like each flake is above each other. So that looks much better. The only problem here, what I don't really like, is that we have the same group of nodes one after each other, which doesn't really make sense to always have that. Like, it's a bit messy. So what we want to do in that case is just to create a group, which you can simply do with Control G. And so inside of the group is exactly the setup we had before, just this localized thing of creating the mask with the Voronoi and then outputting the normal map we want. And so we can just we can just duplicate this group then, so we can do as many layers as we want of those flakes. And you can see, the output is just simply that. I'm also combining them within the group so that it's even cleaner. So you can see that as we go, there's more and more flakes. And then, we just use that in the shader. And that's actually the way I did the car paint for the longest time. I think it's good enough and it looks good. You can go up close and it looks still really nice. But at some point, Blender did an update where they added something called the white noise texture. And I figured that if you go outside on the street and try to look at the car paint of a car, you will actually have a hard time seeing each individual flakes. And so that's a good thing to start using the white noise, which basically creates, and it's really hard to see here, but it basically creates a noise where each pixel will have a different value, so just black and white, and color. So it's just random color per pixel, which means that since most of the time your car paint would anyway have flakes that are sub-pixel size in your final render, you would rather want to use this, so that it's just a much more elegant way, because we don't need to have different groups of flakes and add them together, etc. We just have one node, and that creates all the flakes. And so if we put that in the normal map, then we have this nice grainy effect that we want. But here we start to see something that we didn't catch before, because we didn't have enough, like the flakes were too big. But you can see that the reflection looks just slightly weird, and we can see this effect much more if we start dropping the reflection. And that's something we also had with the previous method. It's just that we didn't catch it, but you can see that the reflection is square, and we don't want that. We want, of course, to have just something that is circular around each point light. And first thing is we need to understand why it does that. And so if we go back to our normal thing here, yes, where is the shader? Here. So if we go back to that, the reason why we have this the square reflection on the other side is because the randomness of each color created by the white noise is from 0 to 1 in both directions, in X and in Y, which means that we can have values that go in like close to 1, 1 or 0, 0, which means a corner of this graph. And that's exactly the reason why it looks like a square, is because the values can be anywhere on that square. So we need to make sure that whatever color is outputted by our random noise is contained within a circle. And so the way we will do that is a bit more technical. We're here. But so, yeah, what we do is that we take our white noise and we will basically check the value of X and Y. So the color that it does random, we can just extract the different colors that will correspond, like for green to Y and for X to red. And so through that, we can define the length of each color on this graph. And so if it goes further than 1, then it means that we are outside of the circle that we want to draw. And so what we do here is that if it's under a value of 1, so if it's within the circle, then we just take the color as it is. If it's not, then we take we scale the vector, so just this color output, we scale it by the power of the length of itself. And that way we can condense everything. And I understand that it's not very easy to get just like that, so I can show you what it changes first, which is that we get this more circular reflection. But also here, this value of -7.5, it's not the best way to distribute the points from a square to a circle, but that's what I find was the most easy to implement, basically. But you can see that if we have a value of 0, then that's the square that we had before. It's exactly the same. And if we start going further, we will actually make the effect even worse by pushing things in the corners. And if we start going down, then we go closer, like the values that are too long, we actually make them shorter and shorter. And so we can condense the light more towards the center. And I think 7.5 just gives us a nicer distribution where there's more light in the center, and then it just fades a bit in a circular shape. And so here, if we put back some roughness, we can see that we have much cleaner reflection, and this just looks much better. And the last thing we want to do here is just to have this noise normalizing function inside of a group, so that we don't need to see all of this math that can seem a bit useless. I mean, we don't want to always have to see it. And so we can just clean the whole shader and have something much nicer like this. Also, here we can put the clear coats within one node, because then we can reuse it. So that's just the mix shader, the glossy, which is the clear coat itself, and the Fresnel. And that's a much better way to have this car paint. Okay, so that was just a first case study, and now let's switch to the carbon fiber, where we suddenly have different challenges, which is, on the first one, everything was coming from randomness. We had this just this fuzzy thing where you have different flakes that the order is very random. Whereas here we have something that is much more organized, because we have this fiber that goes in specific direction. So again, we will rely on the UVs here. I will show you later how to not have to unwrap the UVs yourself, but in this case, we will need those. But before we talk about how to use the UVs and how to make the whole pattern, I think it's important to here again understand what's actually happening. And so the very naive way to do carbon fiber is to think that there's two different colors, because you can see that there is this like lighter gray and darker gray type of lines basically that it creates. And it's tempting to just think like, okay, there's one that has a lighter color and the other one has a darker color. But it's not the case. And so I did a quick setup to show you how it actually works. So here I represented very roughly how carbon fiber is actually made. So let me just switch the world. Yeah. So here, what we will have to do is to use the UV. And for that, we need to understand what does a UV map mean. So basically, a UV map is just the same as if you were trying to wrap a 3D object with fabric or with something like that. So you are able to then derive a 2D shape that you can cut through and then put on your 3D object. But so when it's in this 2D mode, you can put it on a graph basically, which has two directions. So X and Y again, like just up and sideways. And so it's encoded once again in the colors, where you have the red is sideways and green is up and down. And it always have this weird look where you have those colors, and it's a bit not clear when you don't know what it actually represents. But what you can do is to separate the different channels, and then you can see what I mean, where here the UV, so the U basically is encoded in the X channel, and then we have the V, which is the Y channel. Z doesn't matter in this case because we just work in 2D. And so, yeah, you can see that we just have this two normed axes that we will be able to use. And so what we can do, knowing that we have this gradient from 0 to 1, is that we can start playing with functions. Like, for example, here we have a modulo. And so we can repeat this gradient in a bigger or smaller way. And this will help us then creating this type of effect, where first we just create the gradient, but before that, because it's just those three nodes, what we will do on the other axis is that thanks to the snap, we will create a gradient with just solid colors, and we will use that to say every time you use this solid color to shift of a certain amount the base projection, basically. So we end up with something that pushes on the side every time this gradient that we got from the modulo, and this can create this kind of brick effect with just a gradient. And so I just did a node for that, so put everything into a group so that it's easier to work with. And then we can start to duplicate that and do in the other direction as well, and we can start combining them. I'm just using here a mask, basically out of this this node, using a mask which is just black and white to say when it's black it's in one direction, when it's white it's in the other direction, just rotating the weaving of 90 degrees here. And so we can mix that, and we start to see this weaving thing where it's like going up and then it's going under the two that are going in the different axes, then going up again, down, up, and same on the other direction. And that's where it gets interesting, because once we have those gradients, we can actually use them to generate normal maps and just reuse everything we learned before. So we said that you can decide if the reflection will be more on the x-axis or the y-axis, etc. So here what we can do is that we generate a normal map where on one direction we go with just sideways, and on the other one vertical, and we combine those two to create this, that we can just use it as a normal map then and create this effect of just the base weaving, basically. And here we go back to the idea that we have a lot of control, because I can start to play with like the actual shape that I want. Like I can just remove those if I want, put that with ease, and yeah, you can just start playing with how do you want your fiber to be weaved, basically. So that's great. Let's just then do the same, but for the fiber of each thread. So here we use a similar technique, but it's a bit easier. So we just deform a noise. You can maybe see here that we just elongate a noise very long, and this creates just a bit of randomization of black and white stripes, basically. And so here we do the same, but we invert, like when the weaving is going up and down, then we want to go sideways with the fiber, because it does this reflection thing on the other axis. And so we can create this effect that we talked about before, which means that now on one side we have the actual curvature of the thread and also the effect of the fiber, and we just need to find a way to combine those two. Since they never act on the same axis, like the fiber is going one way when the weaving is going the other way, we can simply add them. So here we have like an add vector node, and we are just adding the two. So you can see that we have the weaving and we also have the fiber effect. But to me, this looks like the weaving takes too much importance and we don't see enough of the fiber. So what we can do is to start to add some bias there, which we're just doing like a kind of average, but we give more importance to one of the two just through these simple nodes. And so you can see that here I can start just playing a bit more with what gives more to what I want to give more importance. Like if I put it close to 0, then it will be just the weaving. If I put it much higher, then it will be mainly the fiber. And so around 4, we start to have like a nice ratio, I think, between the two. And yeah, now we just need to add a clear coat, and boom, here we go. We have a nice carbon fiber where we have this weaving and also the fiber effect. And as we said before, now we have a lot of control over this. I can actually show you here if we would go with a different value here. Then we can create a different way to repeat the fiber. So if we have like 0.1, then we have this just 1 by 1 type of carbon fiber, and we were at 0.05. And that's classic 2 by 2 carbon fiber. And yeah, that's great. But we have a problem which doesn't appear here. But if we start adding a sphere, so let's move this one here. Let's just give it a subdivision modifier and smooth it. And so here, if we link the material, we can see that it looks very strange. And the reason for that is that everything is being morphed up to the top and very deformed on any other part of the sphere. And yeah, the reason is just that this is the default UVs that Blender has for a sphere, which is a problem in our case because we would want to have just something cleaner, and we don't want to have to bother doing the UVs ourselves. And so we will see a method which is called the triplanar, where you just base it on your object, but you don't need to. We will recreate the UVs basically, whatever the object. So if I go here, the goal will be to create exactly this. So we want to just project from each main axis. So the Z, the X, and the Y. We just want to say when the object faces this the most, or whatever axis this part of the object is facing the most, should be the axis through which we want to project. Just simply push the texture from that axis. So you can see that we have this U and V with the red and the green, as we talked about before. And so we want to make sure that we have it clean whatever direction the object has. So here, if we start by looking at the UVs of the sphere, you can see why we had this problem, which is that it just looks like it's rotating from the two poles of the sphere, basically. And so we will have to be a bit smarter and not rely on the UVs at all. We will just use the object itself. And for that, what we can do is to use what is called the normal coordinate. So this just gives an indication of where each point of the object is pointing to. So thanks to that, we can start separating it. And we can see that when we ask for the x-axis, it will just give us indication on how much does each part of the object points towards the x-axis. And so in this case, this part of the sphere is very much pointing towards the x, whereas this one not at all. And here it's not just from 0 to 1, it's from -1 to 1. So here everything is dark, but it's actually going from 0 to -1. And we have the same for each axis. So we can see how much does it point towards x and how much does it point towards z. So thanks to that, we can start comparing. Like we can say, okay, does it, if we compare the two, does it point towards x more or to y more? And thanks to this, we can isolate the moments where it's pointing more in direction of x or -x than it's pointing to any direction. And this is just simple comparison. So we just take the absolute so that we don't care that it's from -1 to 1. It just becomes from 0 to 1. And we can compare both. So in this case, x and y. And you can see that it's just saying like this and that are more aligned to the x-axis than the rest of the sphere. And we do that once more with the z-axis and the x-axis. And then we just take the minimum of that, which is the area where it's mainly pointing toward x. So then we can just duplicate this this code or this approach, and we can do the same for the z, for the y, and yeah, we already did it for the x. So that will create us masks that we can then use to create those UVs and say, put this UV in this area, put that UV in this area. So if we go here, we can start constructing our UV space. So here, kind of the same, we have this object texture coordinate. So it's similar to the normal one, and it just gives us data on the object, where things are pointing, etc. And so we can just recreate, we can just isolate, okay, in this case, there's a gradient that goes sideways, it's the y one, and one that goes upwards, that's the z one. So let's just combine them as if it was x and y. And that's creating us this UV coordinate that we just isolate in this square that we said was pointing mainly towards x. So again, we just duplicate the approach a few times to have it for x and z as well. And we start to have some nice UV spaces in every direction. And that's great. But if we start using that on an image, we can see first that it works. And we have minimum stretching, because when it starts stretching a bit too much, then we see that it automatically goes to, okay, the next axis will actually have less stretching by that point. Which means that we always have something that is not too deformed. The problem, though, is that it looks great on those three faces, but if we start going backwards, then it just writes in a mirrored way the Blender logo, and same for down there. The reason for that is that we just project through whatever it sees. So when we project from the x-axis, it's like, okay, just going there. And then, which means that if you arrive on the other side of the sphere, it still projects it the same way. But this time you read it from the outside, not from the inside. So it looks wrong. So we just need to add some logic where we check which side of, if it's in -x or in positive x that we are. And so, yeah, the way we will do that is just to check here. We can just isolate, since we said it was going from -1 to 1 before, we can just say isolate whenever it's superior to 0 or 0.5. And in that way, we can just create the UV like this, and when we switch to the other side, it's like that. So it's always in the correct direction, as if we were rotating it, basically. And then if we do that for the three axes, then everything is always in the correct, like displaying in the correct way And that's great. That's exactly what we want. But we have another problem. And this appears only if we start using a normal map. So here I have a very basic normal map of just a bubble, basically, that we repeat a lot. That's just purely to see the problems and being able to test how to fix it. And so if we start putting that into the normal map and we use a glossy, you can see that it's not very clear if the bubble is correct or not. It looks sometimes like it's concave, sometimes it's convex. It's not clear at all. And so the problem there is that usually when you do your own UVs, it also creates what it's called a tangent space, which is basically telling the normal map node, okay, the right side is that way and up is this way, kind of roughly. And then it's able to say, okay, I know that. And if I take my normal map, I see that I should, the light should react in this way, because if I put my normal map compared to what is the right side or the left side, it should be like this. And here it's super confused. It doesn't know, or it's not that it doesn't know, it's just that the data it has as entry is not correct. It doesn't rely to what we just did. So we need to go a bit further here. I won't necessarily spend too much time on it, but what we can do is that for each of the axes, we always know what is considered up when we look at the face, and so we can then say we know what is the normal of the object, we know what is up. From there, we can derive a perpendicular axis with what is called a cross product. And that can help us create a new tangent space. And so that is what a tangent space looks like, which is, again, very hard to get and wrap your head around, but it's not very necessary. You just need to understand that it was not like the tangent space that it had was not coherent with the UV space we had. And here we are fixing it. On that note, the default normal map node doesn't let you pick which tangent space you want to use. Fortunately, there's this person, Hot Dog Nugget, on Twitter that actually had some problems and then redid a whole node to calculate the normal map action. And so here you can see that they are using their own tangent. I mean, it's the same UV map tangent space, but they have to specify it at some point. So what we can do is to recreate the same setup, but feed in our own tangent input. So in which case, in this case, the one we just created. And now you can see that the bubbles are just acting normally. They are properly bubbly, basically. And so, yeah, we're done. Now we can just use the carbon fiber we did before. And then whatever the direction, the carbon fiber will just properly map to it. And the normals will be correct. So the fiber will always react as it should. And this works for any object. If this time we take the Suzanne, let's just put it on the side. We add a toggle, a subdivision. We smooth it. Now, if we apply the same material, you can see that we don't have to rely on the UVs of Suzanne, the base model. It just figures out by itself, okay, at this moment I should project it that way, at that moment I should project it this way. And yeah, then you never have to bother with your UVs. Of course, if you want something very clean, you wouldn't want to have these visible seams, basically, and you would want to do it by hand. But at least it gives you the option to be just very fast. So, some conclusions. It was a bit nerdy, sorry for that. But yeah, we can learn a few things from that. The first one is that you always need to observe and understand, whether it's from the car paint that we saw with the flakes or with the carbon with the weaving and how the light is behaving. You always need to understand in the real world what happens. and try to see how you can use the tools of modern 3D rendering, whether it's real time or not. What are the tools that you can use? Like normal maps are extremely useful. The second one is that projection is key. As we saw with the UVs and triplanar, it's very important to know how you are laying your texture, even if you're creating this texture yourself. And so you always need to make sure that the projection is correct. And in that case, it's very useful to have this triplanar type of node, because you don't need to spend more time later organizing it. It's just, you can just use it as if it was UVs. And the last thing, it's all about bending light in the end. You just try to replicate a behavior of light on an object. And in that sense, you should really look into normals and how to generate them, how to use them, because they are really the best ally for this kind of stuff. If you thought that this was nerdy, you should head on to shadertoy.com, where people are doing the same, but 1,000 times more advanced, where they actually code stuff. So you can imagine that the nodes that we're doing can just be translated to code, and they actually then are able to go even further because they can have conditions and stuff. But people are doing insane stuff on this website, just creating everything just from a UV grid. They generate whole worlds, and it's very inspiring, and it's a good reference if you want to dive more into shaders overall. If you want to check what we do at my company, you can go at udinbv.com. There's not only Blender stuff, but that's a big part of what we do. And if you have any questions, you can just contact us through the website or from Instagram. Anything, we're always happy to answer. And you can also check Linkage, who was sponsoring the event and this talk. They are providing resources and talents in the automotive industry, the automotive design specifically. And yeah, I think it's what they're doing for the Blender community is really good. Thanks a lot, and I will see you in the next one.